Welcome. In this video we begin section 4.5 Equivalence Relations. Today we are in day 1 where we will examine what is an equivalence relation and we will look at partitions. Let's go. Equivalence relations. Given a set of objects A, a relation R on A is called an equivalence relation if R is symmetric, reflexive, and transitive. We've seen two of these before. We've seen reflexive and transitive. Symmetric, well, we've seen antisymmetric. Remember, antisymmetric meant that the arrows only pointed in one direction. Well, symmetric means every arrow points in both directions. A relation R is symmetric if, whenever AB is in R, then BA is in R as well. This is seen by having arrows that point in both directions. R is reflexive if AA is in the relation for all little a in the set A. And R is transitive if, when AB is in R and BC is in R, we must have AC in R as well. So take a look at these two pictures down below, these two pictures of relations. Is either relation below an equivalence relation? Well, you can probably guess. It's not too hard. On the left, that totally fails everywhere. So be sure you see that relation R1 is not symmetric at all. All of the arrows are only one directional. Reflexive, no, there are no loops. This is how we see reflexive in an arrow diagram. And transitive, there are no triangles at all. So relation R1 totally fails on all three accounts. Relation 2, on the other hand, succeeds. Arrows point in both directions, every node has a loop that points back to itself, and it is transitive. So we can sort of look around there and double check and look for those triangles. Example 1. Define a relation F on the integers by pair AB is in the relation if B minus A is divisible by 4. So look at that, write out several ordered pairs in relation F, and find examples supporting the claim that F is symmetric, reflexive, and transitive. Go ahead and think about this for a couple minutes, then start the video up again when you want to check your work. Let's take a look. So the first one, write out several ordered pairs in the relation. Here are a few that I came up with. In every case, if I take B minus A, I'll get a number that is divisible by 4. Now, the order doesn't actually really matter all that much. For example, in the 420 pair, I really figure 20 minus 4 equals 16, and that's divisible by 4, so 420 is a pair. 24 just reverses that, so I get 4 minus 20, which is negative 16. But negative 16 is also divisible by 4. If 16 is divisible by 4, then negative 16 is divisible by 4 also. And this sort of starts to lead us into finding examples supporting the claim that F is symmetric, reflexive, and transitive. In fact, we just did it for symmetric. 420 is in there, and 24 is in there as well. And maybe you can play around with a few other examples and see, yeah, it looks like it seems to hold. What about reflexive? I had the pair 1, 1 that was in there. And in general, well, you can pretty much see that A comma A for any number is going to be in this relation because A minus A equals 0, and 0 is divisible by 4. So reflexive works also. And then what about transitive? I have these last three pairs that show the transitive property. 1 and 5 are related, 5 and 25 are related, and it also happens that 1 and 25 are related as well. So there's evidence. It's not a proof, but there's supporting evidence that this relation F is symmetric, reflexive, and transitive. It looks like, and in fact it is the case, that F is an equivalence relation. Example 2. Define relation R on the integers by pair AB is in R if the sum A plus B is divisible by 4. So this looks pretty similar. The only difference between this and the previous relation was now we're adding the two elements. So what do you think? Is R symmetric, reflexive, transitive? Take a couple seconds and test each one. Answer yes or no and see what you think. Pause the video and then In a few minutes, start up when you're ready to check your work again. Let's see. Is it symmetric? Yes, it is symmetric. And you can probably see that this is true in general. If 4 divides the sum a plus b, then certainly 4 divides the sum b plus a. A plus b and b plus a are the same thing. Is it reflexive? No, all you need is one example. 1, 1 is not in the relation, so this relation is not reflexive. It's true that there are pairs, like 6, 6, that are in the relation, but that doesn't matter. As long as you have just a single example of a pair, a number with itself that is not in the relation, then this relation is not reflexive. And is the relation transitive? No. And you can probably come up with an example. Here's one that I found. 1, 3 is in the relation, 3, 5 is in the relation, but 1, 5 is not. 1 plus 3 is 4, 3 plus 5 is 8, but 1 plus 5 is 6. Equivalence relations and partitions. If R is an equivalence relation, and AB is in the relation, we say that A and B are equivalent, or A is equivalent to B. In relation to the picture to the right, which elements are equivalent to 1? So here's 1. There's the loop, so 1 is equivalent to 1. Oh, maybe I'll start writing a set here. 1 is equivalent to 1. And then I look at where it's connected. It's connected to 3, and it's connected to 5. So 1, 3, and 5. All of those are equivalent to 1, and they are all equivalent to each other as well. Which elements are equivalent to 2? And that's the other triangle that lives in there, the 2, 4, 6. Relation R2 induces the partition of something. What is it? So it takes the numbers 1 through 6, and in fact it splits them into different classes, different sets. It's the set 1, 3, 5, and the set 2, 4, 6. So this relation, R2, it's broken up all the elements of A into equivalence classes. So 1, 3, 5, those are all equivalent to each other. 2, 4, 6, those are all equivalent to each other. And the set as a whole is the combination of 1, 3, 5 and 2, 4, 6. So every equivalence relation ends up creating a partition. And conversely, if you have a partition, that is essentially the same thing as an equivalence relation. Again, let's consider the equivalence relation f on the integers by a comma b is in f if b minus a is divisible by 4. What numbers are equivalent to 1? Equivalent to 2, 3, 4? Find the partition of the integers that is induced by f. All right, take a minute, see what you can do. Start again to check your work. All right, so which numbers are equivalent to 1? So I'm going to write down 1 here. And I need that the difference of something and 1 is divisible by 4. So 1 and 5, that difference is divisible by 4. And if I add 4 more, there we go, and add 4 more to that, 13, and on and on and on. But in fact, I can subtract as well. So -3, -7, there we go. So here's a set of numbers that are all equivalent to 1. Which numbers are equivalent to 2? Again, I can play the same trick. Let's add 4, then add 4 again, and 4 again, and so on and so on. And all those numbers are going to be equivalent to 2. And I can work backwards. -2, -6, and so on. Let me write out the other sets as well. Here we go. Okay, so we have the 4 sets of numbers that show us the equivalence classes. All the numbers that are equivalent to 1, all the numbers that are equivalent to 2, all the numbers that are equivalent to 3, all the numbers that are equivalent to 4. part number 2, find the partition of the integers induced by f. Well, this is it. I should just draw one big set of parentheses around this whole thing. And there is my partition of the integers based on this particular relation. Another way you could write this out, maybe something like this. I'll write the set. Those things that are equivalent to 1, that's the set of numbers that look like 4k plus 1, such that k is an integer. And the set of numbers that are equivalent to 2, that's really 4k plus 2, such that k is an integer. And the other ones are similar also. There we have it. There is the partition of the integers induced by relation f. Here's our last example. Let S be the set of all permutations of the letters A, B, C, D in any order. For example, here are 2 different examples of permutations, A, B, D, E, C, and E, A, D, B, C. So just any way you can mix up those 5 letters, those are all permutations. It turns out that the number of permutations is 120. For what it's worth, just by the way, that ends up being 5 factorial. Define relation R on this set of permutations by saying that 2 permutations are in the relation if X is a cyclic permutation of Y. For example, here's what I mean by a cyclic permutation. Let's say, I'll just make something random, D, B, A, E, C. There is a permutation, and I can make a cyclic permutation of that by maybe starting at A and then moving to the right and then wrapping around from the left. So I can make A, E, C, D, B. So these 2 permutations are cyclic permutations of each other. This relation, is it reflexive, symmetric, transitive? How about reflexive? Is a permutation a cyclic permutation of itself? Yeah, sure, you could say it is. I can imagine rotating that around 5 times, I'd come back to itself. Is it symmetric? Well, looking at these 2 examples above here, if the second is a cyclic permutation of the first, then I can keep cycling around and get back to the first again. So yeah, it's symmetric. And is it transitive? If there was a third thing out here, and the first was a cyclic permutation of the second, and the second was a cyclic permutation of the third, well, yeah, then the first would be a cyclic permutation of the third. Yep, so kind of not doing anything serious, but just general intuition, yes. It does seem as though this relation is reflexive, symmetric, and transitive. This looks like an equivalence relation. So, find the set of elements in S that are equivalent to DABCE. What are all the permutations equivalent to DABCE? Well, we can start with that thing itself, DABCE, and then take that same permutation and cycle it so you start with A. So the order is the same, just looping around, but now starting with A. And then do the same thing starting with B, and then starting with C, and then starting with E. And if I continued and I started the next one with D, I'd end up back where I started. So this set, that is the set of elements in the permutations that are equivalent to DABCE. So R is an equivalence relation on S, so it induces a partition of S. How many lists are in each part? And how many parts are in the partition? Last time, take a minute or 2, think about this question, see if you can answer that, and then start the video again to check your work. All right, so the first question is just immediate from our work up there. There are 5 lists in every part. All the permutations are just permutations of 5 letters, and there are 5 ways of cycling those letters around. The next one might be a little more tricky though. How many parts are in the partition? Well, we know that there are 120 partitions in total. Each part has 5 partitions in it. So when I take 120 divided by 5, I get 24. So it turns out that if I make the partition based on this relation, then my partition consists of 24 parts, and each part has 5 elements in the sense. Okay, in the next lesson, we will look at techniques for proving that certain relations are equivalence relations, but this is a good place to stop our introduction.